The 2022 Nobel Prize in Physics was awarded for one of the strangest experiments ever documented. It went to Alain Aspect, John Clauser, and Anton Zeilinger for their work demonstrating quantum entanglement, a theory that predicts the fates of tiny particles, like photons or electrons, can be linked across arbitrarily long distances. It seems absurd. Albert Einstein famously doubted the theory was complete, calling it spooky action at a distance. What I want to show you in this video is a really fun way of understanding the work of these Nobel Prize winners that emerged in the late 90s and early 2000s, which frames the experiment as a collaborative two-player game, where in theory the players can gain an advantage in this game, but only by sharing a pair of entangled quantum particles. And when you actually play this game in real life, well, what you get is pretty spooky. Amy and Brian walk into a room where there are two coins. Amy's coin is red on one side and yellow on the other. Brian's is orange and green. They each take their coins, move to opposite sides of the world, and flip them. After seeing which color they got, Amy and Brian will each immediately, without being permitted any time to communicate with each other, say a number, either 0 or 1, based solely on the colors they see on their coins. Now let's look at those colors for a moment, since they're relevant to the rules of the game. Notice that red and orange are quote-unquote similar colors. Orange and yellow are also similar colors, as are yellow and green. But red and green are sort of opposite colors. When Amy and Brian flip their coins, if they get similar colors, they win if they both say the same number. For example, if Amy flips yellow and Brian flips orange, which are similar colors, they'd win if they either both say 0 or both say 1, but they'd lose if one of them says 0 and the other says 1. On the other hand, if they get dissimilar colors, i.e. red and green, they only win if they say different numbers, and they lose if they say the same number. Amy and Brian are allowed to strategize with each other in advance as much as they'd like. And as you'll see by the end of the video, a crucial part of their eventual strategy is going to be to share a pair of entangled quantum particles. Now, before we get to that, let's figure out the optimal way to play this game without any quantum shenanigans. There's a very simple way to see that it's not possible to guarantee a victory. There are 4 cases for the colors on Amy and Brian's coins: red and orange, yellow and green, or red and green. Suppose Amy is going to choose 0 if her coin lands on red. Ideally, Brian's choice for orange should then be the same as Amy's choice for red, 0, since red and orange are similar colors. This would mean Amy's choice for yellow should also be 0, because if they get yellow and orange, they need to say the same number. And once again, this means Brian's choice for green should also be 0, because if they get yellow and green, they need to say the same number. But now, what if they get red and green? Those are dissimilar colors, which means they need to have different numbers to win. But instead, they would both be choosing 0, which means they'll lose. So in the 3 out of 4 cases that aren't red and green, they win. That's a 75% success rate. Now, this is a pretty boring strategy. They're both just going to choose 0 no matter what the colors are. And there are other, more fun strategies that also give a 75% success rate. But there will always be at least 1 out of 4 cases where a loss is inevitable. So 75% is the best you can do. Or at least that's what you might think. But you see, real-life experiments have demonstrated a statistically significant higher success rate. And these experiments have been conducted in the proper conditions with truly random coin flips, and in an environment where the two players are far enough away from each other and really do have to submit their answers immediately, before any hypothetical communication could happen between them at the speed of light. The only explanation we have for this higher win rate is the theory of quantum entanglement, and a clever strategy that makes use of it. So how does quantum entanglement give you an advantage in this game? Well, this question is kind of useless unless we know what quantum entanglement is. In this video, we'll approach that concept from the quantum computing perspective, which means we're not going to discuss the actual quantum physics involved, like the spin of photons and electrons, but rather focus on the mathematical model for that physics. And once we learn the rules to that mathematical model, it'll be able to explain what's going on in theory. We need to start by learning about the basic data type of quantum computation. While normal computers store data using bits, values that could be either 0 or 1, quantum computers use qubits, which, like regular bits, can also either be 0 or 1, but in addition, they can exist in what's called a superposition of 0 and 1, meaning they're sort of partially 0 and partially 1. A common way of representing this is with a unit vector in 2D space, where the horizontal axis is 0 and the vertical axis is 1. Just a quick note about the notation here, this angle bracket stuff is called a ket, and for now you can just think of it as signifying that it's a quantum state. Now, the weird thing about qubits is that when we observe or measure them, the superposition collapses and we really will see either 0 or 1. If the vector points more towards the 0 axis, then when we measure the qubit, it'll be more likely to come out as 0. And if it points more towards the 1 axis, then the measurement will be more likely to come out as a 1. Specifically, the probability of seeing a 0 is the length of the horizontal component of the vector squared, and the probability of seeing a 1 is the length of the vertical component of the vector squared. So, for example, if the state vector of our qubit is at a 45-degree angle between the 0 axis and the 1 axis, this would make the horizontal and vertical components both equal to square root of 1/2. And if we square that, it's 1/2. So measuring the qubit now would give us exactly a 50% chance of seeing 0 and a 50% chance of seeing 1. Real quick before we proceed, I just want to mention that in reality, the components of these vectors can also be complex numbers. But we won't be needing that for this video, so it's safe to simplify our view and stick to real numbers. Now, to manipulate the state of a qubit, there are various operations you can do, which take the form of either rotating the state vector by a certain angle or reflecting it about a certain axis. In the real world, each possible rotation or reflection you can think of corresponds to some physical operation you could do to a quantum particle that alters the state in that way. But with just one qubit, you can't do anything all that interesting. All of this fancy stuff just amounts to a glorified random number generator, since the state vector is going to be at some angle, and then measuring the qubit gives either 0 or 1, each with some probability according to that angle. The magic happens when you add a second qubit. Now, you might expect that with 2 qubits, you get 2 state vectors, one for each qubit. But that's actually not how it works in theory. And what troubled Einstein is that the actual theory predicts some pretty weird stuff. And so he thought the theory was incomplete. Essentially, this weirdness is what we call quantum entanglement, and it's the basis for quantum computation. Since we're already approaching things from that angle, we'll proceed by accepting this theory and seeing what we can do with it. The theory says there are operations you can do to cause qubits to become linked to each other, meaning their measurement outcomes become correlated. So it's not enough to think about each of the qubits individually. Instead, we have to think about the entire 2-qubit system, with, again, a single state vector. Only this time, it's 4-dimensional. Each of the 4 dimensions corresponds to one possible measurement outcome of the 2 qubits, 0, 0, 0, 1, 1, 0, and 1, 1. The 2 qubits exist in a superposition of all of these states at once. Now, 4 dimensions is one too many for us to visualize naturally, so instead we'll be viewing the 4D state vector via its projections onto 2 2D planes, one spanned by the 0, 0 axis and the 1, 0 axis, and the other spanned by the 0, 1 axis and the 1, 1 axis. By the way, the reason why we're visualizing it like this is because the plane on the left represents the states where the second qubit is 0, and the plane on the right represents the states where the second qubit is 1. Splitting things up in this way is going to be helpful for us later. Now, just like with one qubit, when a 2-qubit system is measured, the superposition collapses to one of the 4 possible outcomes: 0, 0, 0, 1, 1, 0, or 1, 1. And the probability of each of those outcomes is, again, the length of the component of the state vector that points in that direction squared. Let's see how those probabilities change as we modify the state. Notice, by the way, that the 2 yellow arrows aren't necessarily staying on the blue unit circles this time. In our visualization for a single qubit, the arrow did stay on the unit circle because it was a unit vector in 2 dimensions. With our visualization for a 2-qubit system, the state is still a unit vector, but it's in 4 dimensions, meaning it lies on a 4-dimensional hypersphere of radius 1 instead of a unit circle. So I'll remind you that this visualization is still depicting just one vector, but you're seeing how that 4D vector looks when projected onto these 2 2D planes. Just like with one qubit, every possible rotation or reflection in the 4D space corresponds to some physical operation you could do to a pair of quantum particles that alters the state in that way. Okay, we're now ready to see how Amy and Brian can use quantum operations in their coin flipping game. Remember, they start the game together in the same room, so they have time to strategize before traveling to opposite sides of the world. And part of that strategy is going to include preparing some physical stuff. First, Amy and Brian will create a pair of qubits, A and B, which start in the state 0, 0. Next, they'll do a single qubit operation called Hadamard applied to A, which changes the state like this. And now they'll do a 2-qubit operation called C0 applied to A and B, which changes the state like this. We could spend a bunch of time delving into what exactly these 2 operations are and how they change the state in general, but for this video, all you need to know is that there's some operations, you can apply them to a pair of qubits, and the resulting state vector looks like this. It points a little bit towards 0, 0 and a little bit towards 1, 1. This specific state actually has a special name. It's called the EPR state, named after a revolutionary thought experiment involving this exact 2-qubit state by Albert Einstein, Boris Podolsky, and Nathan Rosen that caused Einstein to question the theory of quantum mechanics. Hopefully, the rest of this video will prove to you why that's the case, because Amy and Brian are about to use the EPR state to do something strange. They're now ready to go their separate ways, and since we're working purely in theory here, now is when we're going to simply accept what is, on the face of it, a pretty bizarre assumption, which is that the qubits Amy and Brian just entangled will stay entangled when they move to opposite sides of the world, meaning operations that Amy and Brian might apply to their own qubits individually still affect the 2-qubit system the same way across arbitrarily long distances as they would if the qubits were right next to each other. Okay, so back to the game. They each have a coin, and they want to say the same number as each other, 0 or 1, if and only if they flip quote-unquote similar colors. So how can they use these entangled qubits to gain an advantage? Well, first of all, think about what would happen if they were to measure their qubits right now, while they're still in the EPR state. They'd get either 0, 0 or 1, 1, each with 50% probability, since the state vector points towards each of those outcomes equally. So crucially, in the current state, they'll always get the same answer as each other, even though we don't necessarily know which one. But this isn't enough to give them an advantage over the best classical strategy. As we saw before, if they always say the same answer as each other, they'll lose every time Amy flips red and Brian flips green, or 25% of the time. But importantly, Amy and Brian can still apply single qubit operations to their own qubits before measuring them. And just so we're on the same page about what a single qubit operation means in the context of a multiple qubit system, if you go back to thinking about the state vector for a single qubit again, an operation on that qubit looked like a transformation in the plane spanned by the 0 and 1 axes. In a multiple qubit system, the same operation will cause that same transformation to happen, but the transformation gets replicated among all possible configurations of the other qubits. Remember, in this visualization we're using, the plane on the left represents states where the second qubit, B, is 0, and the plane on the right represents states where B is 1. So for example, if Amy applies a rotation operation to qubit A, what that looks like in the two-qubit system is two separate rotations, one in the plane on the left and one in the plane on the right. So starting from the EPR state, which was sort of partially 0, 0 and partially 1, 1, a rotation to qubit A moves the state vector more towards the states 1, 0 and 0, 1, meaning if Amy and Brian measure now, they'll be more likely to get different answers from each other than they were before. Now, we can call this way of visualizing things Amy's perspective, since it's good at depicting what happens when Amy applies a rotation to qubit A. But it's also useful to see how things look from Brian's perspective, where the axes are switched so that the plane on the left represents states where A is 0, and the plane on the right represents states where A is 1. And not to be misleading, Amy and Brian don't actually get to see the underlying state of the qubits. This is all happening under the hood as a mathematical model for what happens when they eventually measure. That being said, when Brian applies a rotation to his qubit, B, it moves the state counterclockwise in both of these planes. But with the axes switched, this same operation looks like a clockwise rotation from Amy's perspective. You can check the math, it is in fact the same angle in the opposite direction. Likewise, a counterclockwise rotation of qubit A from Amy's perspective appears clockwise from Brian's perspective. This is exactly the property that they'll leverage to gain an upper hand in the game. And one last thing before we get to what that strategy actually is, we can simplify our picture here a little bit. We don't really need two 2D planes to represent the state if all Amy and Brian are going to do is apply rotations to their respective qubits. Because as we just saw, any rotation that Amy or Brian could do amounts to shifting the two-qubit system more towards a state where their measurements will give the same answer, or more towards a state where their measurements will give different answers. For our game, we don't care what the answers actually are, only whether they're the same or different. So we can think about the state vector as existing on a single 2D plane, with a same answer axis and a different answer axis. A rotation by Amy moves the vector counterclockwise in that plane, and a rotation by Brian moves the vector clockwise in that plane. So here's Amy and Brian's best strategy. They're going to take the four colors on the coins, red, yellow, orange, and green, and assign each of them a different angle, 90 degrees, 45 degrees, 67.5 degrees, and 22.5 degrees. It'll make sense why we're using these exact values in just a moment. Right after Amy and Brian flip their coins, before measuring their qubits, they'll each apply the rotation for the color they got to their qubit. Let's see what happens in the case where Amy gets red and Brian gets orange. The qubits start in the EPR state, which lies entirely on the same answer axis. Amy does a rotation by 90 degrees, moving the state vector entirely towards the different answer axis. But Brian does a rotation by 67.5 degrees, moving the state vector back towards the same answer axis, making a 22.5 degree angle. Remember, since red and orange are similar colors, Amy and Brian need to say the same answer in order to win, and the laws of quantum mechanics say the probability of that happening when they measure their qubits is the length of the horizontal component of this vector squared, which is cosine of 22.5 degrees squared, roughly 85%. Okay, pretty good. What about the other cases? Well, suppose Amy flips yellow and Brian flips orange. Starting from the EPR state, Amy would rotate by 45 degrees, but Brian would rotate by 67.5 degrees, moving the state vector back down to make a 22.5 degree angle below the same answer axis. Again, they need to say the same answer as each other in order to win in this case, since yellow and orange are similar colors. And the chance of that happening is, once again, the length of the horizontal component of this vector squared, which is cosine of 22.5 degrees squared, or roughly 85%. It's the same story in the case where Amy gets yellow and Brian gets green. This time, the vector would end up here, the same position as the first case, and thus they end up with the same chance of success. Now, in the final case, where Amy gets red and Brian gets green, they need to say different answers to win. But look where the state vector ends up. Amy does a rotation by 90 degrees since she sees red, but Brian's rotation only moves 22.5 degrees in the opposite direction, meaning the vector is left pointing mostly towards the different answer axis this time. It's only 22.5 degrees away. The probability that they say different answers is the length of the vertical component of the vector squared, which again is cosine of 22.5 degrees squared, the same 85% as before. So in all cases, Amy and Brian have a roughly 85% chance of winning the game using this quantum strategy, whereas we saw before that the best possible classical strategy only gives a 75% chance of winning. So that's it. That's their winning strategy. Now, there are a couple of questions you might ask here. For example, why exactly these 4 angles? The short answer is they give you the exact same chance of winning in all 4 cases of the coin flips, which turns out to be optimal for giving the best chance of success. There are in fact many other combinations of 4 angles that can beat a 75% win rate. However, if you do the math, you'll find that no strategy gives a better win rate than the one I demonstrated. But perhaps the most pressing question of all is what happens when you try to actually do this strategy in real life? Well, that's exactly what the 2022 Nobel Prize in Physics was awarded for. The 3 winners were involved in experiments that actually played the game we learned about in this video around the 1970s and 80s. Albeit, at the time, these experiments weren't yet framed as a quote-unquote game. That interpretation developed a bit later, in the late 1900s and early 2000s. But the bottom line is, using the game interpretation, they won more than 75% of the time, more often than should be possible without quantum entanglement, proving that what Einstein called spooky action at a distance might just be the best explanation we have for how the universe really works. The actual name of the game, by the way, is the CHSH game, named in part after one of the 2022 prize winners, John Clauser. But I also just thought it's worth mentioning that the other 3 letters are for Michael Horn, Abner Shimoni, and Richard Holt, who were also highly involved in theorizing about and formulating these experiments. Anyway, what I find compelling about this story is that it's one thing to predict some weirdly amazing result about the universe by thinking about wiggling vectors in 4-dimensional space. But on its own, this can seem ridiculous. As I've been mentioning throughout the video, Albert Einstein, a pioneer of quantum mechanics, never accepted this math as complete. I want to share a quick clip with you of a conversation I had about this with Professor Ryan O'Donnell, a prominent quantum computing researcher and theoretical computer scientist. Also, I want to extend a huge thanks to him for taking the time to talk with me and discuss the concepts for this video. It was really a huge help.
He and Podolsky and Rosen had this position paper where they espoused the pretty natural belief that an experiment in one physical location should only depend on the status of physical objects in the neighborhood of that particle. You can imagine if you were trying to write like a physics simulator of the universe and like at time tick t, you wanted to like understand like what is the physical state at this location, like it ought to only depend on like the nearby physical states. And this viewpoint is called local realism, and this experiment violates it. If you're the universe and you like want to like be a universe simulator, you really need to remember that there's like something happening at like this part of the universe and something happening at this part of the universe that are like correlated. It's philosophically, frankly, kind of unsettling or unsatisfactory, but
the universe works in mysterious ways, and I personally think this is just one of the coolest intersections of theory and practice in science. I hope you learned something, and thanks for watching.